Today we're going to talk about algebraic expressions. And the main thing about algebraic expressions that is important is variables is a letter that represents a variety of different numbers. And if you understand that we're basically using a variable to represent different numbers, we just have to know what that variable stands for. So in an expression, we do not have an equal sign. So these are all examples of expressions. Now, the question that we might ask ourselves is, are variables always represented by x? And the answer is no, they're not always represented by x. Sometimes we can use y, z, or any letter at all, as long as we know what that letter stands for. So if we are talking about a length of a TV, we might want to use L, as demonstrated here. So now let's look at problems where we would substitute. And if we look at this example up here, if we have 6 plus 2x, we have a variable, remember that represents a number, and it tells you that the number is 10. So if we put that number, and I use parentheses to kind of show that representation. There's my replacing the x with what it says it equals, and then I can do the math, and that's just order of operations. So that's 20 plus 6, so we get 26. And so we get the answer to that problem. The next problem is a distributive problem, but before we distribute, we could replace the x with the 10. So in this case, we could have 2. So in this case, we could have 2 with the 10 replaced with the x equals 6, or plus 6. And if we do this math with parentheses first, we get 2 times 16, which equals 32. Now if you do it distributive-wise, we have the x plus 12, that's distributing, and we replace the x with the 10, we get 20 plus 12, and we get the same answer. So you can look and do these problems. So in these particular problems, we have 2 letters to replace. And so we can replace the x with 3, so I'm going to use parentheses to show the replacement, and then we can use the 8 to replace y. If we do the math, we get 21 plus 16, and 21 plus 16 is 37. The next problem has a little bit more complication to it, but the substitution is still the same. We have 6, and x happens to be 3, minus 8, all over 2, 8, minus 3, minus 8. And now we just do order of operation. So I'm going to do my multiplication first on top. So that's 18 minus 8. There's my numerator. And I do left to right. This is 16 minus 3 minus 8. So 16 minus 3 minus 8. And when I finish doing this problem, I'll get 10 over, and that happens to be 11, so 5. And 10 over 5 will equal 2. In these problems, we're looking at forming expressions from words. So we have these expressions right here. So what we want to be able to do is understand that if you're reading something, pay close attention when it's a subtraction. And so if you look at these problems and you read what it says, look what it says to form, it makes much more sense than just writing what you see. All other problems, you can pretty much write what you see. So if you look down here at the problems that are given for checkpoint, the first problem, the product of 6 and a number. Product means multiplication, 6, and a number is just n. The next problem, a number added to 4. So we have a number added to 4. Notice how I'm writing them is simply by reading exactly because they're not subtraction. 3 times a number increased by 5. So 3 times a number increased by 5. So if we look at D down here, twice a number subtracted from 12. So now this subtraction means I'm going to take this twice a number and subtract it from 12. So this is how we subtract from 12. And then our final problem here, the quotient of 15 and a number. Quotient means division, so we're dividing 15 by n. So now what we want to determine is if we have an equation, we want to know if it's equal. So if we give you a number, so in this case we have an equation, and we want to know whether this equation is equal or true. And to do that, we substitute and see if it's true. So here is our first equation right here. And so I'm going to substitute the 6. Erase this. I'm going to substitute the 6 where the x goes, because that's what it says, substitute. And I'm going to see if this is true or not. So this is 36 minus 3. Does that equal 42? It does not equal, so this is not an equation. Or 6 is not a solution. So an equation is a solution that works or makes it true. So let's check this next one. So if I have 3 as my y value, so I'm going to substitute 3 in where y is. Everywhere I see a y. And I'm going to solve. In this case, this is 6, this is 18, and this is 15 minus 3. 15 minus 3 is 12, and this also is not equal. So this is not a solution. Okay, the whole purpose of what we're doing is creating symbols that describe the real world, or equations. And so if we look at this, this is often called a formula. So the equations that are already created from real world examples are formulas. In this case, we have a formula right here for the temperature of based on the number of chirps a cricket has per minute. So from that formula, if we know how many chirps there are per minute, which we do right here, we can substitute that into the formula and get the temperature, which is 64 degrees. So at 80 chirps, we get 64 degrees. So creating algebraic expressions or algebraic equations basically try to represent the real world. So here's an example of a data from age at marriage rate and the probability of divorce. And so what we want to do with this is the formulas that are created are right here. So when someone is under age of 18 compared to someone over 25. And what we want to do is look at or answer these questions based on those formulas in the graph. So the first question is, use the appropriate formula from example 6 on page 9, which is this one, to determine the percentage of marriages ending in divorce after 15 years when the wife is under 18 at the time of marriage. So we are looking at this formula under 18, so we have D, so A is D equals 4n plus 5. And all we have to know is how many years, n standing for the number of years. And in this case, it happens to be 15. So if we put the 15 into our formula, we get 65. That's the percentage of divorces. Now you can look at the graph to get that same answer, or use the formula that's created from the graph. Let's look at B. B says, use the appropriate line graph in 1.1, page 8, to determine the percentage of marriages ending in divorce after 15 years when the wife is under 18 at the time of marriage. So we'll go to the graph then, and make it so the percentage of ending in divorce after 15 years for under, which is the red line, it looks like it says about 60%. About 60%. So the question that we need to look at is, does this value given by the mathematical model underestimate or overestimate the actual percentage of marriages ending in divorce at 50 years as shown in the graph? It overestimates by 5%.